Since the 1960s, we've seen one of the most incredible trends in all of human history, the exponential growth of computing power. Our machines have just gotten ridiculously powerful, while at the same time shrinking down to almost nothing. I mean, this relentless march of progress has basically defined our entire modern world. So, what happens when it just stops?
Well, that's kind of what's happening. The very miniaturization that has been the engine of our tech revolution is getting dangerously close to its absolute physical limit. We are about to slam into a wall. And this wall, it's built out of the very atoms that make up our universe.
To get why, you gotta peel back the layers of a computer. It's kind of like a Russian doll. You've got your computer chips, and inside those you have modules, and inside those you've got logic gates. But if you keep zooming in all the way down, everything, and I mean absolutely everything, boils down to one single fundamental component: the transistor.
At its heart, a transistor is just a tiny, tiny switch. That's it. When it's on, it lets a little bit of information, a flow of electrons, pass through. We call that a 1. When it's off, it blocks them. That's a 0. These simple on-off states, these little bits, are the foundation for literally everything your computer does, from sending a text to streaming a movie.
And we have gotten absurdly, almost unbelievably good at making these switches small. A typical transistor today is only about 14 nanometers wide. Now, to put that into perspective for you, that is about 500 times smaller than a single red blood cell. We are literally building our modern world on technology at a near atomic scale. And this is where our problem really begins. Because as we shrink these transistors down to the size of just a handful of atoms, the nice predictable classical laws of physics we all rely on, they start to get, well, weird. That reliable on-off switch starts to flicker because of this bizarre phenomenon called quantum tunneling.
You see, in the quantum world, tiny particles like electrons, they just play by a completely different set of rules. An electron that's heading towards a blocked-off passage, our off switch, doesn't have to stop. It can, for all intents and purposes, cheat. It can just poof, appear on the other side, tunneling right through a barrier that should have stopped it.
So you can see the issue, right? If your switch can't reliably stay off, your zeros and ones get all jumbled up, your data gets corrupted, your entire system just breaks down. We've pushed classical computing so far that its most basic parts are becoming obsolete. We are at a real physical wall.
But what if, and this is the revolutionary idea, what if instead of fighting all this quantum weirdness, we just embraced it? This is the whole concept behind quantum computing. Scientists are now building a whole new type of machine that actually uses these strange properties to its advantage, and it all starts with a new kind of bit.
So check this out. This is the core difference. A classical bit, the kind in your phone, is like a light switch. It is definite. It's either a 0 or a 1. That's it. A quantum bit, or qubit, is on another level entirely. It can be a 0 and a 1 at the exact same time. It's not a switch anymore. It's a whole spectrum of possibilities happening all at once.
Now, how is that even possible? Well, this incredible ability is powered by two main principles of quantum mechanics that are famously counterintuitive. They almost feel like magic, and they're called superposition and entanglement.
Okay, so superposition basically means that as long as you're not looking at a qubit, it exists in this fuzzy cloud of probability. It's a little bit of 0 and a little bit of 1 all mixed together. But, and this is the crazy part, the instant you measure it, the moment you look at it, that whole cloud collapses and the qubit is forced to pick a side. It becomes either a definite 0 or a definite 1. And here is where the mind-blowing power comes from. If you have, say, 4 classical bits, they can only represent one combination of numbers at any given time. But 4 qubits that are in superposition, well, they can represent all 16 of those possible combinations simultaneously.
But this power, it grows exponentially. So let's just scale that up. What happens if we go from just 4 qubits to maybe 20?
With just 20 qubits, you can store and process over 1 million values at the very same time. This isn't just about being faster, it's a totally different way of computing. It gives you a level of parallel processing that is just flat out impossible for any classical computer.
All right, and the second property is entanglement, and somehow it's even weirder. You can actually link 2 qubits together so their fates become intertwined. So if you measure one and find out it's a 0, you instantly know its entangled partner is a 1. And this works no matter how far apart they are, across the room or across the galaxy. It's this strange connection that lets quantum computers handle incredibly complex calculations.
So, what is all this incredible power actually for? Now, it's really important to get this. A quantum computer is not going to be replacing your laptop anytime soon. Think of them as very specialized tools. They're designed to solve a very specific class of problems, problems that are basically impossible for even the world's most powerful supercomputers today.
So what kind of stuff can they actually do? Well, their power is going to revolutionize things like finding a needle in a cosmic haystack, searching through massive databases. And this is a big one, breaking modern cybersecurity. Also, simulating complex molecules to discover brand new medicines and materials.
Yeah, let's stick with that for a second. The encryption that protects all of our stuff, our banking, our emails, government secrets, it all relies on creating mathematical problems that are just incredibly hard for normal computers to solve.
For a normal computer, trying to crack a modern encryption key would take years, maybe even centuries, of just trial and error. But because a quantum computer can try all the possibilities at once, a powerful one could do it, well, in a breeze.
But on a more positive note, one of the most exciting uses is simulation. It's really hard to accurately simulate things like molecules and proteins on a normal computer. But think about it. What better tool could you possibly have to simulate a quantum system than an actual quantum system? This could completely unlock new drugs, new materials, and a much deeper understanding of our universe.
The truth is, we're just at the very beginning of this. We honestly don't know if quantum computers will just stay as a highly specialized tool for scientists, or if they're going to spark a revolution on the same scale as the very first computers.
A quote from the source material for this explainer I think just says it perfectly. We have no idea where the limits of technology are, and there's only one way to find out. For all of human history, this is what we've done. We've pushed against our limits, we've discovered new principles, and we've built tools that changed absolutely everything. And right now, we are standing at another one of those moments.
So as we stand here, right at the dawn of this new age of computing, the question is still out there. Are we just building a better, more specialized calculator? Or are we about to unlock a whole new chapter for humanity itself? The future is unwritten, and that right there is what makes this so incredibly exciting.